doing for a final. You're like, what do you want to go over? Of the whole course, people might say, can we do that domain and range again from chapter 14? Oh yeah, we can. There's a radical or a natural log. But there's one more thing from this sheet. It doesn't say level curves. What does it say? Those are functions of x, y, and z. Alright? Those are functions of x, y, and z. And they want you to find the what? Describe. Oh good, we don't have to draw these. Okay? Describe the level, not level curves, but level what? Surfaces. And that's not a typo. But they do put this, at the end of 14.1, level surfaces. When they ask for that, then you have a function of x, y, and z. Oh, we get it. Now there's a third level. A function of x and y, you can have level curves. Take those level curves and you build something three-dimensionally. A function of x, y, and z, you have level surfaces, like a family of what? Spheres or something. But then, if we did this part, that would be what? Fourth dimension? And fourth dimension is just so hard to even try to grasp or just sketch that. We won't be sketching it. Okay? Yeah, you're like, wow. Because you'd be going into fourth dimension. All right. But now, let's look at the first one. What do they got? X plus 3y plus 5z. Remember, we just got to put down a word or a couple words just to describe these. We'll do each one of these. These go quick. Describe the level surfaces. Surfaces. Make sure you see that word surfaces. Because we're not going to say, oh, something like this. I wouldn't say, oh, they're parabolas. Parabolas aren't cylinder, surfaces, right? It's got to be something three-dimensional. So what do you think the first step is? Let z equal to, and you go, there's no z this time. We'll let the function of x, y, and z be the k. If you want to make up another letter for this, I don't think you can. You can call it w. But the function of x, y, and z, let that be a k. So pretend this is a k. This is how we do it. Let this be k now. Now think of that family of all those surfaces. What are they? What would be the surfaces? K equals x plus 3y plus 5z, and you got different k values. K can be a 1, k can be a 2, k can be equal to -1, -2, a bunch of what? A bunch of planes. Bunch of planes. I'll put family of planes. See, you get a family of planes. Love the surfaces. Alright? Yeah, these go pretty quick. How about what's the next one? X squared plus 3y squared plus 5z squared. This is why section 12.6 was so important. We now have to recognize this stuff. Those surfaces from section 12.6. X squared plus 3y squared plus 5z squared, and they said for k greater than 0, right? So let this be a k. So close. Spheres need to be perfect, all the same coefficient. So the football thing, what do you call it? An ellipse? Ellipsoids. So this would be a family of ellipsoids. Alice, good job. Because Nate, she goes, spheres, and then she goes, wait a minute, they want to be spheres because that's a 1, that's a 3, that's a 5. She goes, oh, ellipsoids. Footballs. Blimps. X squared minus y squared minus z squared. And he said for k greater than or equal to what? Section 12.6. I see two minuses. Hyperboloids of how many sheets? Two sheets. So it's a family of hyperboloids, you can abbreviate. Family of hyperboloids, put how many sheets? So I'm going to put 2s. It's a family of hyperboloids of 2 sheets. This is the one I need you to be careful on the problem set or on a test. You can get people. Function of x, y, and z, y squared plus z squared for k greater than 0. Oh, it happens all the time. Like on a multiple choice, and people choose circles. First of all, a surface is not a what? So a circle is not a surface, right? Right? So what are these? Think of this. K, there's only two variables in there. What was going on in 12.6?
Cylinders.
They're cylinders. Very good. Circular cylinders, right? They're centered on which axis? Which letter's missing? I mean, if you wanted to go further, but we can just say a family of cylinders or a family of circular cylinders. If you want to go even further, you can make it's a family of circular cylinders all centered on the what? X-axis. And now you're really thinking fourth dimension here, because that's what you're thinking. But it's a family element, right? It's a family element if you want to try it. Now sketch it. What is it? They're all cylinders, concentric cylinders. They're all inside of each other, right? There you go. No, I'm not going to say it. But anyway, right. Yes. Family of cylinders centered on the x-axis. Hey, cool. Great job with this. Hey, I'm not going to pass this out. 1, 2, 3, 4. We're now going to do section 14.3. So once again, it saves time that you got a worksheet with a table. You have to copy the table. I'll put the table on the board, but you don't have to copy the table from the board. It's already there. We'll work with this. These are called partial derivatives. You're welcome. Partial is a great section. You're welcome. We'll spend a good amount of time in this section. No rush for this section. There's 20 things. We're going to find partial derivatives, but we're going to find them from equations. We're going to find partial derivatives from graphs, from level curves. We'll find them from three-dimensional graphs. We'll find partial derivatives. We'll make sense of what they are. So there's different ways we're going to find these partial derivatives. Let me write this down right here. This is in section 14.3. Partial derivatives. All right. So, my first example, how about this? Function of x and y equals x squared y cubed. And you bet the first thing you saw in here was a table, right? We'll get to that table in a moment. I just want you to see how cool partial derivatives are. What's this variable z? We're going to find partial derivatives. So we can find the partial of f with respect to x. Let me read that to you again. This is going to be the partial of f with respect to the letter x. So what you do is, you differentiate everything here only with respect to that letter x. That means you're going to hold the y constant. Let that y be constant there. What will you get for f of x? Well, let me get this out of the way. I apologize. What will be fx for this problem? What will be the partial of f with respect to x?
2x y cubed.
So you said this would become 2x, but they held the constant right next to it, multiplied like it was a 5, and they got 2x y cubed. Good job. Hey, is there other notation? Yeah. Do you remember back in Calc 1 when you were like df, dx, derivative f with respect to x? We can do that here. We use delta, so the d is really a delta. Delta f, delta x, if we want to put that, but it's another notation. Oh, delta f. But you'll notice even in the textbook, they use that Greek letter delta there. Looks like a D, just write a D if you want. It looks like a D. I was wondering if you could find, oh, and another thing, sometimes they write this. It's the partial respect to x of the function of x and y. They might put the function of x and y still next to it. Right? Or here they might write what? Delta f, delta x, and then next to it put the, and you're getting a solution. But just like, remember, you sometimes wrote f prime of x, but sometimes you just put a y prime. This is like just putting the y prime. So, I use the easiest notation, which would be this. Can you find that? That would be the partial derivative with respect to what?
Y.
Y.
So 3y square x squared.
Yeah, and they call it the first partial derivative. Because in a second, we'll do second partial derivatives. So the first partial with respect to y, I get
3y squared.
3y squared to the x squared stays, and I'm going to go in alphabetical order. 3x squared y squared?
Mm-hmm.
Okay, I'll get this out of the way. What the heck is this? That's called a second partial derivative. You got it. To get there, she goes, you got to go through here first. So the first thing is you had to take this and take the first partial with respect to x. Now you're going to take the derivative of this expression right here with respect to what?
Y.
Y. So what is the second partial with respect to x, y right there? What do you get? 6xy squared. What they did, they differentiated with respect to y, this thing. Right? And they kept the x constant. True? Yeah, on that note, can you all find fyx? So in order for me to derive all this with respect to x, keep y constant.
6x.
Now this is interesting, I'm getting the same what?
6x squared.
Interesting, they're both the same. Do you think that happens every time? It does. And there's a mathematician, whoever comes up with first gets the name to it, like Pythagorean theorem and stuff, although Pythagoras was not the first one to prove that. Other cultures have done it. This Clairaut's theorem says that fxy will always equal what? fyx. If, as long as they're continuous functions. As long as they're continuous functions. Which you can even, feel free to read about that in the textbook. No, fxx does not equal fyy, but I was just curious, can you get fxx? So what's fxx? You'll notice it does not have to equal fyy. What's that? fxx? 2y cubed. You want to do fxxx? Or 3 x's? Third partial derivative? 0.
When you're doing fxxx, are you considering from the second one or the?
That's right. So I'm going to start here first.
Okay.
So it's like, this came from here, right?
Uh-huh.
To do this, I have to take the derivative of this expression partially with respect to x.
Okay.
They call it a second partial derivative. So you have to use this. We differentiate that with respect to x, and we just got the what? 2y cubed. Now that you say, all right, you're like, okay, I got to take this expression and take the derivative of that partially with respect to x. They call it a partial derivative. Which you get what?
0.
A constant. Very good. Got this is equations. But it's like, you go, yeah, you gave me a simple one. What about one with radicals? What about one with a sine or a cosine? We'll get into that. We'll get into those later. We'll practice them. I have tons of practice problems and kind of practice on that. I got another worksheet. Okay, what's fyy? I'm just curious. 6. fyy would be 6x squared and then just a what?
Y.
A y? Hey, but I'll go back. Isn't this a three-dimensional graph? So you're like, well, what is that geometrically? What is this geometrically? A partial with respect to x would be the slope at a point in the direction of the positive x-axis. It'd be the slope of this. It's a surface, right? The slope of the surface, any particular point that you plot in the direction of the positive x-axis. What's the partial with respect to y? First partial derivative. Because isn't that, remember back in Calc 1, isn't derivatives just finding slope? Slope of a tangent line. So it'd be the slope, fy. Partial with respect to y would be slope in the direction of the positive y-axis. You can find this at any point. Now, we used to say slope of a tangent line. Now I could say slope of a tangent plane to the surface. Do you follow me?
Mm-hmm.
But this is what this stuff is geometrically. Cool section, because now we're starting to think, ooh, we can take surfaces now, we get a slope in any direction. That's where we're going, right? Before we were just kind of stuck in two-dimensional space going, oh, there's the curve, get the slope, right? We're here, get the slope. Now we're talking about a surface. You go to the point, you go, I can get the slope in any direction. But right now, we're only doing the direction of the x-axis or the y-axis. In Calc 1, what did second derivative represent? Concavity, right? Concavity. So now you're thinking, oh, I can take a surface and think if the surface is what? Concave up, like a cup, right? Or maybe concave down, like an upside down trout, like a surface. So that's what's going on. You go, oh, when you have like an fxx. And we'll talk about, I got some practice problems like that. I had to put some images on here that were three-dimensional, but we'll still be able to look at it. Cool. But what we're going to do right now, everyone, we're going to find partial derivatives from a table. We did it from equations, right? But just briefly, I give you a simple equation. We're going to want more advanced stuff in a second. But now we got that down, can we find partial derivatives from tables? How do we find a partial derivative from a table? And you bet. Eventually, we're going to find a partial derivative from a three-dimensional graph. So when I have a table here, let's see what we got here. V, what's V stand for?
Velocity?
Speed. Okay, that's the speed. What's T stand for?
Time.
T is the time duration in hours. And they said H is function of V and T. Boy, multi-variable function. And H represents the height of what? Wave heights, right? Cool. These are wave heights. So these represent wave heights. Here come the wind speeds. And this is the V. And I'll put these down here. What do you got? 20, 30, 40, 50, 60. There's a nice table here, right? I'll come across here and go like this. That's why I want to give you sheets. You wouldn't have to copy this. What's those times? Now there's the wind velocities. Now what's the time duration? And the wind's been blowing for what? Let's see. 5 hours, or 10 hours, or 15 hours, or 20 hours, or 30 hours, right? Etc. It kept going, right? That's good enough. And in this, you have all these numbers. I don't have to copy all these numbers. You got copies of this table, right? But I'll just put the number right here. Let's see. 4010. F of 4010 is at 21. Do you agree this is true? F of B comma T. F of 40 comma 21 is equal. Whoops. 40 comma 10 is the number 21. You all agree? F of 40 comma 10 is 21? We can see it. So what can you interpret that for me? When the velocity is what?
40.
Yeah, what were the units for the wind speed? What were the units? Knots? 40 knots? But it's been blowing for how long?
10 hours.
10 hours straight consecutively. The height of the waves is what? 21 feet. This is in feet. Now I'm going to go to another place, way down here when it was 60, comma 30, and I'm looking at this number and wow, that's a 62. So we're saying when the wind speed is 60 knots and the wind's been blowing for what? 30 hours, look at the wave height, 62 feet. So that's what we're saying. That's where this is a function of two variables, B and T. Well, we're going to find partial derivatives. The first one they want you to find is, well, of course they do this. This isn't a partial derivative. Can you find f of 40 comma 15? All right, so let me go there. What's that number right there in the chart? 25. I'll put some numbers in here. That's a 25. What's next to it? 28. This is 16. This is 36. Is that right? I think that's all we need. Now what's f of 40 comma 15?
25.
Can you interpret that again? When it's what?
Not the wind velocity is 40
40
knots.
knots?
For
Blowing how long?
15 hours.
15 hours straight. Like a hurricane. Wave heights are now at 25 feet. Okay. But that's not a partial derivative. This one is. Can you estimate, and I'm going to put that word estimate, because we don't have an equation, do we? With an equation, we can find it exactly. Plug in the numbers. We have a table. We're going to estimate the partial derivative a V, 40, 15. Hey, can we put some other notations here? What else does this mean? Delta F, delta what? Delta V? Does everyone agree? You want to call it FZ? What else is it? Delta Z? Delta V, right? There's a reason I'm doing this. We're going to estimate this because we don't have the formula. So how do you estimate this? We just go back to, well, we'll just do change in the Z values over the change in the V values. That's how we'll do it. That's the only way we can estimate it from a table. So what we're going to do, because we're estimating we're doing a partial derivative from a table, I don't have an equation, I'm just going to do change in the Z values, or the F values, right? Which are the heights, right? Change in heights over the change in, what's that variable? The V's. What about that other variable? What's the other variable? T. T is being held what? Constant. T is being held constant. Okay. So that's what we'll do. Here, I'll get this out of the way. This is what we're going to do. Change in F values or change in V's at what point? So I say, first of all, I'm going to 40, 15. Let's circle that so we get our eyes. It's got to be right at that point. Now, if I can make a change, should I use numbers like this over here and do, I can do change. Where are the V's? Oh, here are the V's right here. So, should I use numbers like this, and this, and the number over here? When you're trying to estimate it at a point, use the closest numbers possible, right? What's the closest numbers I see to that 25? The 36 and the 16. So I'll do change in, these are the F values, these are the heights, over the change in the V's. So what's one way I can do this? I can do 36 minus 25 over 50 minus 40. Will that work? Okay.
But these are the closest values if you take, right?
That's right. So this is one thing I do. You got it. Take the closest you can to the 25. So one thing I could do is, for change in F over change in V, I could say 36 minus what? 25, change in F. Now what corresponds with that? 50 minus 40. This would be one answer. And then I'll go to your art in a second. I just want to see, what do I get there?
11 over 10.
What's that as a decimal? 1.1. But I only took this side. Can I take the other side?
Yeah.
I just want you to see, what if I took the other side? Because that would still be an estimate. By the way, that's a decent answer. You know, it's an estimate. Can you try the other side? What would you get? 25 minus 16, right? F values. Change in F. 25 minus 16 over the change in the corresponding velocities, that's a 30. 40 minus 30. What do you get there, though?
0.9.
Yeah, that's 9 over 10. What's that as a decimal?
0.9.
29. Now, both of these are great estimates. What would be even better, though? To take these two numbers and take the what?
Mean.
Average. And that's what the textbook does. So if you want to practice problems out of the textbook, that's what you're going to see. You're going to do one side, and then the other sides, and then take the average. So what's the average of these two?
1.
So I'm going to put, just you can go up here and go, hey, the average of this turns into 1. Now, when we talk about units, what was this? 1 feet per, what was this?
Hour.
No, V, what was V units? So 1 feet per knot. So can we talk about this, like what does this really mean? Here's what I would say. Because partial derivatives, isn't that a rate of change? Oh, it's slope, but it means rate of change. Okay. So when the velocity is 40 knots and the wind's been blowing for 15 hours straight, all right, the wave heights are increasing 1 feet per knot, right? When I hold the time duration constant at that point. Does that make sense? Yeah, rate of change. So you're like, the actual height of the wave is increasing 1 foot. Per increase of what? Per increase of 1 knot in the wind speed. Is that at all points? No, only when what? When it's been blowing for 15 hours at 40 knots. Do you follow me? And that's what we're talking about in terms of rate of change. Cool? Love it. Hey, one more. One more problem. We're going to wrap it up. We got that. What's the other one they want?
Estimate f of t.
Yep. I'm gonna erase all this. Estimate F, what's the subscript right there?
T.
Ooh, T. Same point though. So everyone, where's my formula? No formula, I got a table. How do you do this from a table? Change in F values over the change in the
T value.
T values at that point. So let me get this. I can use that same point right there, but now which way am I going? Change in F over change in T. Change in F over change in T, and we'll take the average. By the way, could I do this? Could I just go this minus this over this minus this? Wouldn't that be a decent estimate? Trust me, free response, that's a great answer. Okay, I just wanted to make sure, if you're looking in the back of the book, who I call Bob, Bob's going to do what? One side, the other side, and take the average. So I'm going to do that. Let's try it. 28 minus 25 over 20 minus 15. Also, I can do what? 25 minus 21 over 15 minus 10. Did I hit that right? And what are these fractions? 3/5. This is,
450.
what's that as a decimal?
0.6.
0.8. What's the average?
0.7.
0.7. Now what's the units? Feet per hour. So can we interpret that? Oh, what's going on with, this is rate of change. It's like the wave heights are increasing what? 0.7 feet per increase of 1 hour in extended duration of time when the wind's been blowing for 15 hours straight at 40 knots.
Isn't it 0.7 knots, right? Not feet.
This thing right here, because we're taking a partial derivative for F with respect to T. What was F's units? So let's come over, and I like good question.
Okay.
What was F's units? F is H.
Oh,
F
okay.
is height. So it's still going to be feet, but now we're just talking about per hour while you held the other variable constant.
Gotcha. Okay.
Cool? Hey everyone, we didn't finish 14.3, but we will finish it up next time. Have a great weekend.